In 2012, astronomers confirmed something terrifying. Andromeda, our nearest large galactic neighbour, sitting 2.5 million light-years away, is coming straight at us. Not drifting nearby, not passing in the distance. Coming directly at us at 110 kilometers per second. That's 250,000 miles per hour. And there's no avoiding it. No escape trajectory. No way to stop what's coming. In approximately 4 billion years, the Andromeda Galaxy will collide with the Milky Way in one of the most violent events the local universe will ever witness. But here's what no one tells you. This collision isn't some distant abstract future event. It's already begun. The gravitational tendrils of both galaxies are already reaching out, already pulling, already reshaping the space between us. Everything you know about the night sky is about to change. And the strangest part? Earth might actually survive it. Look up on a clear autumn night, away from city lights, and you'll see it. A faint, fuzzy oval in the constellation Andromeda. Most people who notice it at all assume it's a cloud, a nebula, some distant cluster of stars. It's not. That fuzzy patch is the Andromeda Galaxy, a spiral galaxy containing over 1 trillion stars, more than twice as massive as the Milky Way, and so large that even from 2.5 million light-years away, it appears 6 times wider than the full moon in our sky. Most people know Andromeda is another galaxy. What they don't know is that it's already profoundly affecting us. The gravitational influence between Andromeda and the Milky Way has been shaping the orbits of stars, the distribution of dark matter, and the trajectory of dwarf galaxies for billions of years. For over a century, astronomers describe galaxies as island universes, isolated systems floating through the cosmic void, rarely interacting, existing in pristine separation. That narrative was wrong. Galaxies are dynamic and deeply interactive. They pull on each other across millions of light-years of space. They exchange stars and gas. They collide, merge, and transform. And recent discoveries between 2012 and 2024 have completely revolutionized our understanding of what's coming. The Andromeda-Milky Way collision isn't starting in 4 billion years. It's already begun. The story starts in 2002, when astronomers using the Hubble Space Telescope began a painstaking project, measuring Andromeda's sideways motion across the sky. This is harder than it sounds. Andromeda is moving toward us at 110 kilometers per second. We've known that since the 1920s thanks to spectroscopy showing its light is blue shifted. But is it coming straight at us? Or is it also moving sideways? If Andromeda has significant sideways motion, what astronomers call tangential velocity, then it might miss us. A cosmic near miss. Close call, but no collision. If it has almost no sideways motion, direct hit. For 10 years, Hubble tracked the positions of individual stars in Andromeda, measuring their motion relative to distant background galaxies. The precision required was extraordinary, like measuring the width of a human hair from 2,000 miles away. In 2012, the team led by Roland van der Marel at the Space Telescope Science Institute published their results. Andromeda's tangential velocity, 17 kilometers per second. That might sound significant, it's not. At a distance of 2.5 million light-years, that sideways motion is essentially negligible. Translation: Andromeda is coming straight at us. Computer simulations were run, modeling billions of years of gravitational interactions, incorporating dark matter, stellar dynamics, and orbital mechanics. The simulations were run thousands of times with slight variations in initial conditions. The result was unanimous: head-on collision. Inevitable, unavoidable, certain. Refinements in 2019 and 2024 with better data narrowed the timeline, 3.8 to 4.2 billion years from now, with a margin of error of only plus or minus 50 million years. On cosmic timescales, that's pinpoint precision. But here's what's truly strange. This isn't the first time these galaxies have interacted. Evidence is mounting that Andromeda and the Milky Way have been gravitationally bound for their entire existence, circling each other like binary stars, slowly spiraling inward over billions of years. We've detected tidal streams, unusual stellar motions, and dark matter distributions that suggest a long history of gravitational interaction. We're not strangers meeting in the void. We're long-lost siblings finally coming home. Over the next hour, we're going to witness a cosmic drama that unfolds over billions of years. A story of two galaxies, their inevitable collision, and the strange, violent, beautiful transformation that follows. This isn't a story of destruction, it's a story of transformation. And we're going to experience it in 5 acts. Act 1, the approach, now through 2 billion years from now. We'll explore what's happening right now as the galaxies close the distance, how the night sky will change, when humans will first notice something is different, the slow build of gravitational tension. Act 2, first contact, 2 to 4 billion years from now. The moment outer spiral arms begin to interpenetrate, when gas clouds collide at hundreds of kilometers per second, when the largest starburst in local group history ignites. Act 3, the collision, 4 to 5 billion years from now, the main event. The core of Andromeda plows through the Milky Way. What happens to Earth, to the Sun, to our solar system, whether we survive or are flung into the darkness of intergalactic space. Act 4, the merger, 5 to 7 billion years from now. Multiple collisions as galaxies can't escape each other. The slow, grinding process by which 2 spiral galaxies become one elliptical galaxy. The birth of Milkomeda. Act 5, the aftermath, 7 to 10 billion years and beyond. What the merged galaxy looks like, how it fits into an expanding, emptying universe. The final fates of stars, black holes, and ultimately, reality itself. By the end of this journey, you'll understand something profound. The universe doesn't end, it transforms. And the strangest, most hopeful part of this entire story? If humanity, or our descendants, survives long enough, we might not just witness this transformation, we might thrive in it. Let's begin. Before we can understand the collision, we need to understand the dancers. And Andromeda is unlike anything in our local cosmic neighborhood. Let's start with the raw numbers. Andromeda contains approximately 1 trillion stars. The Milky Way, about 200 billion. That means Andromeda has 5 times as many stars as our galaxy. It's not just bigger, it's in a completely different weight class. Spanning 220,000 light years from edge to edge, Andromeda is more than twice the diameter of the Milky Way. If you could see it with your naked eye at its true extent, not just the bright core but the faint outer regions, it would appear 20 times larger than the full moon. It would dominate the autumn sky. But sheer size doesn't tell the full story. Mass matters more than star count. And Andromeda is estimated to be roughly 1.5 to 2 times as massive as the Milky Way when you include dark matter, with ongoing refinements as measurement techniques improve. That gravitational heft is what makes this collision inevitable. Andromeda's gravity well is deep, and we've been falling into it for billions of years. However, here's where things get interesting. Andromeda is also older. Its stellar population is more evolved. The galaxy went through its major star formation phase billions of years ago. Today, most of its stars are middle-aged to elderly, yellow, orange and red stars that have been burning steadily for eons. The Milky Way, by contrast, is younger and more active. We still have vigorous star formation happening in our spiral arms. We have more gas, more dust, more raw material for creating new stars. In boxing terms, Andromeda is the larger, heavier, more experienced fighter, but it's past its prime. The Milky Way is smaller, younger, and hungrier. That matters when galaxies collide. But there's something else about Andromeda that most people don't know. It's already a merger survivor. When astronomers used the Hubble Space Telescope to study Andromeda's core in detail, they discovered something unexpected. It has a double nucleus. 2 concentrated regions of stars orbiting each other at the galaxy's center. This is the smoking gun evidence of a past collision. Sometime in the last few billion years, estimates range from 2 to 4 billion years ago, Andromeda collided with and consumed another large galaxy. The double nucleus is the remnant of that merger, 2 galactic cores that haven't quite finished combining. Andromeda is a cannibal, and we can see the evidence written in its structure. Using spectroscopy, astronomers have also identified multiple stellar streams, long ribbons of stars stretching through Andromeda's halo. These are the shredded remains of at least 10 dwarf galaxies that Andromeda has consumed over its history. Each stream tells a story, A smaller galaxy ventured too close, got caught in Andromeda's gravity well, and was slowly torn apart by tidal forces. Its stars were stripped away one by one, stretched into long streamers that now orbit Andromeda like the rings of a planetary grave. Andromeda isn't some pristine, peaceful island floating through space. It's a battle-scarred veteran, a gravitational predator that has grown fat by devouring its neighbours. And now it's coming for us. But before you think this is a story of a monster consuming an innocent victim, let me tell you about the Milky Way. The Milky Way is no innocent either. If you watched our previous video exploring Earth's rare position in the galaxy, you already know some of this story. But let's recap with the Andromeda collision in mind, because our galaxy's history shapes what happens when the two collide. The Milky Way is a barred spiral galaxy, a spiral with a rectangular bar structure cutting through its core. It spans approximately 100,000 light-years in diameter and contains between 200 and 400 billion stars, with recent estimates favouring the lower end of that range. We have four major spiral arms: Scutum Centaurus, Carina Sagittarius, Perseus, and Norma. These aren't rigid structures but density waves, regions where stars, gas and dust temporarily bunch up as they orbit the galactic centre. At our core sits Sagittarius, a star, a supermassive black hole with a mass of approximately 4 million times that of our Sun. That sounds massive, but compared to Andromeda's central black hole, which weighs in at 100 to 200 million solar masses, our black hole is practically a lightweight. When those two black holes eventually collide, but we're getting ahead of ourselves. The critical thing about the Milky Way is that it's younger and more gas-rich than Andromeda. We have approximately 10% of our mass in the form of interstellar gas, the raw material for star formation. Andromeda has much less, perhaps 3 to 5%. This gas is crucial. When galaxies collide, it's the gas that collides, not the stars. Stars are so far apart that even during a galactic collision, direct stellar collisions are extraordinarily rare. But gas clouds, they slam together at hundreds of kilometers per second, compress, heat up and ignite in massive bursts of star formation. The Milky Way's abundant gas supply means that during the collision, we'll contribute more than our weight class would suggest to the resulting starburst. We might be smaller, but we're packing more fuel. But here's something most people don't realize. The Milky Way is still growing. We're still consuming smaller galaxies right now. The Sagittarius dwarf elliptical galaxy is currently passing through the Milky Way's disk for perhaps the third or fourth time. Each passage strips away more of its stars. In another billion years, it will be completely dissolved, its stars fully integrated into our galaxy. We're also in the process of shredding and consuming the Canis Major dwarf galaxy. The large and small Magellanic Clouds are gravitationally bound to us and may eventually be consumed. And there are dozens of smaller dwarf galaxies orbiting us like moons around a planet, future meals. The Milky Way is a cannibal too. In fact, the 2018 Gaia spacecraft data revealed that the Milky Way's halo, that diffuse sphere of old stars surrounding the main disk, is largely composed of stars stolen from other galaxies. The Gaia-Enceladus merger, which we discussed in the previous video, added roughly 600 million stars to our galaxy about 10 billion years ago. We are not innocent victims in this story. We are participants in an ongoing cycle of galactic cannibalism that has been happening since galaxies first formed. But there's one more key difference between us and Andromeda: age. The Milky Way formed approximately 13.6 billion years ago, shortly after the Big Bang. But our major growth phase, the period of rapid star formation and galaxy building, happened more recently than Andromeda's. We're still, in galactic terms, relatively young and vigorous. Andromeda went through its main sequence of development earlier and faster. It's larger because it had more mergers early on. It's older because it matured sooner. When the collision happens, we're not just bringing fewer stars to the fight. We're bringing youth, gas and dynamism. Andromeda is the experienced heavyweight. The Milky Way is the hungry upstart. And there's a third dancer in this cosmic ballet that could change everything. Zoom out with me for a moment. Let's look at the bigger picture. Andromeda and the Milky Way are not alone in the cosmic void. We're part of something larger, the Local Group. The Local Group is a gravitationally bound cluster of galaxies spanning approximately 10 million light-years across. It contains at least 54 confirmed member galaxies, though the exact count keeps growing as we discover more faint dwarf galaxies lurking in the darkness. But despite having 54 plus members, the Local Group is dominated by just 3 large galaxies: the Milky Way, 200 billion stars; barred spiral Andromeda M31, 1 trillion stars; spiral triangulum M33, 40 billion stars; spiral. Everything else, the other 50 plus galaxies, are dwarfs. Small, faint, irregular collections of a few billion stars at most. They're gravitational hangers-on, satellites orbiting the big three like moons around planets. For decades, astronomers assumed the Andromeda-Milky Way collision would be a binary event. 2 galaxies, 1 collision, simple dynamics. But recent observations have complicated the picture. Triangulum, the 3rd largest galaxy in the Local Group, is also on a collision course. It's currently 750,000 light-years from Andromeda and closing fast. Computer models suggest that Triangulum might collide with Andromeda first, about 2.5 billion years from now, before the main Andromeda-Milky Way collision. Or it might not. The dynamics are incredibly sensitive to initial conditions. This is what physicists call the 3-body problem. With 2 objects, like the Earth and Moon, you can calculate orbits precisely. They're predictable, stable, mathematically elegant. Add a 3rd massive object, and the system becomes chaotic. Small changes in position or velocity lead to wildly different outcomes. Prediction becomes nearly impossible beyond a certain time horizon. Some computer simulations show Triangulum colliding with Andromeda first, then the merged Andromeda-Triangulum system colliding with the Milky Way, creating an even more massive galaxy. Other simulations show Triangulum getting flung out of the Local Group entirely during the collision, ejected into intergalactic space like a stone from a slingshot. Still other simulations show Triangulum orbiting the collision site, waiting to be consumed later, or even surviving independently if it's moving fast enough when the main collision occurs. The probability? Roughly 50-50 that Triangulum participates directly in the merger, and this matters enormously. If Triangulum joins the collision, it adds 40 billion more stars to the mix. More importantly, it adds another supermassive black hole at its core, about 3 million solar masses. 3 black holes, instead of 2, changes everything about the final merger dynamics. 3-body black hole interactions are chaotic. They can accelerate the final merger, or they can create bizarre binary systems where 2 black holes orbit each other while the 3rd orbits both of them. There's even a possibility, small but non-zero, that one of the 3 black holes could be ejected from the system entirely, flung out at thousands of kilometers per second, carrying its own retinue of stars. A rogue black hole wandering the cosmos. But beyond the big 3, there are all those dwarf galaxies to consider. During the collision, the gravitational chaos will disrupt the orbits of every dwarf galaxy in the Local Group. Some will be flung into intergalactic space, exiled forever. Others will be captured by the merging system, falling into the maelstrom and adding their stars to the mix. Still others will have their orbits drastically altered, sent careening through the Local Group on new trajectories. The Local Group as we know it, this small cluster of galaxies, this cosmic family, will be completely destroyed and reorganized. From 54 plus galaxies, we'll go to perhaps 1 large elliptical galaxy, Milkomeda, surrounded by a handful of survivor dwarfs. Everything else will be either consumed or ejected. The family reunion will be violent, chaotic, and transformative. This isn't a collision between 2 isolated objects. This is the complete restructuring of our corner of the universe, and it's already begun. The gravitational tendrils of these 3 massive galaxies are already reshaping orbits, already pulling gas and stars, already setting the stage for what comes next. So now you understand the players. Andromeda, massive, old, experienced, already a merger survivor. The Milky Way, smaller, younger, gas-rich, still hungry. Triangulum, the wildcard that could make everything more chaotic. But understanding the players is just the beginning. Now we need to understand the approach. What happens in the next 2 billion years as the distance closes and the gravitational dance intensifies? Because the collision doesn't start in 4 billion years. It's unfolding right now, in ways both subtle and profound. Let's examine the approach. Let me tell you how we became absolutely certain this collision is inevitable. Because the science behind this prediction is genuinely remarkable. For over a century, astronomers have known that Andromeda is approaching us. In 1912, Vesto Slipher measured Andromeda's spectrum and noticed something unusual. Its light was blue-shifted, not red-shifted. In an expanding universe where almost everything is moving away from us, Andromeda is moving toward us. By measuring the degree of blue shift, astronomers calculated the approach velocity, approximately 110 kilometers per second, or about 250,000 miles per hour. That's fast by human standards, about 700 times the speed of sound. But across 2.5 million light-years of space, it's actually quite slow. At that rate, Andromeda covers the distance to Earth in about 4 billion years. But knowing something is approaching doesn't tell you if it will hit you or miss you. Imagine a car driving towards you in the distance. You can measure how fast it's coming closer by watching its headlights get brighter. But to know if it will hit you, you need to know, is it also moving sideways? Is it going to pass by, or is it on a collision course? That's the question astronomers needed to answer about Andromeda, and it's extraordinarily difficult. Measuring sideways motion, what astronomers call proper motion or tangential velocity, requires watching an object's position change over time relative to more distant background objects. For nearby stars, this is straightforward. They visibly shift position from year to year, but Andromeda is 2.5 million light-years away. At that distance, even motion at hundreds of kilometers per second produces almost imperceptible changes in position. To detect it, you need to measure shifts smaller than the width of a human hair viewed from 2 miles away. That requires the Hubble Space Telescope. Starting in 2002, a team led by Roland van der Marel at the Space Telescope Science Institute began a long-term project. They identified specific bright stars in Andromeda's halo, stars far from the galaxy's bright core, where precise measurements were possible. Then they waited. Every few years, Hubble would observe these same stars again, measuring their positions with exquisite precision. The telescope's stability and resolution made this possible. Ground-based telescopes couldn't achieve the necessary accuracy due to atmospheric distortion. By 2012, after a decade of observations, they had enough data. The results were published in the Astrophysical Journal. Andromeda's tangential velocity is approximately 17 kilometers per second, with a margin of error of about plus or minus 15 kilometers per second. That might sound like significant sideways motion. It's not. At 2.5 million light-years distance, moving sideways at 17 kilometers per second is like walking across the street while running towards someone a mile away. The sideways component is negligible compared to the forward motion. The conclusion was inescapable. Andromeda is coming almost directly at us. Not perfectly head-on. That 17 kilometers per second sideways motion means the initial impact won't be perfectly centered, but close enough that a collision is certain. The team then fed this data into sophisticated computer simulations. These weren't simple calculations. They modeled the visible mass of both galaxies, stars and gas, the dark matter halos, much more massive than visible matter, the orbital motions of both galaxies around their common center of mass, the gravitational influence of other local group galaxies, general relativistic effects on the largest scales. They ran these simulations thousands of times, varying the initial conditions slightly each time to account for measurement uncertainties. Every simulation ended the same way: collision. The timeline, 3.8 to 4.2 billion years from now, with the most likely date being approximately 4.0 billion years. Refinements in 2019 using additional Hubble data narrowed the margin of error. Updates in 2024 using Gaia spacecraft data for Milky Way stellar motions improved the models further. The collision is now predicted with a certainty that rivals our predictions of solar eclipses. The margin of error is plus or minus 50 million years, which sounds large but represents only about 1% uncertainty on a 4 billion year timeline. Barring something completely unforeseen, like an encounter with a massive dark matter structure we haven't detected, this collision will happen. The universe has set the timer, and it's counting down. But what will this look like? Not from space, not from computer simulations, but from Earth. What would someone standing on our planet actually see as this collision unfolds? Let's take a journey through time. Right now, year 0. Step outside on a clear moonless autumn night. Look toward the constellation Andromeda. If you're in a dark location away from city lights, you might see a faint fuzzy oval, barely visible, easy to miss. That's Andromeda. Even though it's 220,000 light-years across, twice the width of the Milky Way, it's so distant that it appears small and faint. Its core spans about 3 degrees across the sky, 6 times wider than the full moon. But most of that extent is too faint to see with the naked eye. What you perceive is just the bright central region. To the unaided eye, it's underwhelming, a cosmic giant reduced to a barely visible smudge. In 1 billion years, the view has changed. Not dramatically, you'd need to know what you're looking for, but noticeably. Andromeda is now approximately 1.4 million light-years away, nearly half its current distance. It appears almost twice as large in the sky and significantly brighter. The fuzzy patch has grown. If you photographed it with long exposure, you'd see spiral arm structure starting to resolve. But here's the problem. By 1 billion years from now, Earth has other concerns. The Sun is about 10% more luminous than it is today. That might not sound like much, but it's enough to push Earth's climate past several critical tipping points. Average temperatures have risen by 40 to 50 degrees Celsius. The oceans are evaporating at an accelerating rate. Water vapor, a potent greenhouse gas, amplifies the warming in a runaway feedback loop. Earth is becoming Venus. Any humans still living on Earth at this point are doing so in underground habitats, domed cities, or have long since migrated to Mars, the outer solar system, or other stars entirely. The surface is hostile to complex life, but if someone were still there, still looking up, they'd see Andromeda growing in the night sky like a slow-motion cosmic predator. In 2 billion years, Andromeda now dominates the autumn sky. It's 800,000 light-years away, 1/3 its current distance, and spans 15 to 20 degrees across the sky. That's 30 to 40 times the diameter of the full moon. The spiral structure is clearly visible even to the naked eye. 2 prominent spiral arms can be traced from the bright core outward into the darkness. Dust lanes, dark regions where interstellar dust blocks starlight, create texture and depth. Andromeda no longer looks like a distant object. It looks like a neighbour. The brightest regions of Andromeda now outshine all but the brightest stars in Earth's sky. If you extended your arm, Andromeda would span the width of your hand held at arm's length. But Earth itself is, by this point, almost certainly lifeless. The Sun's luminosity has increased by 20%. Surface temperatures average over 100 degrees Celsius. The oceans have completely evaporated. The atmosphere is mostly water vapor and CO2, creating crushing greenhouse heat. Any liquid water exists only deep underground, if at all. The Earth is a dead rock still orbiting a brightening star, and in the sky above its scorched surface, Andromeda looms ever larger. In 3 billion years, Andromeda is now 500,000 light-years away, 1/5 its current distance, and filling 40 to 50 degrees of sky. It's no longer just an object in the sky, it is the sky. The spiral arms stretch from horizon to horizon. Individual bright star clusters within Andromeda become visible as distinct points of light. The dust lanes are prominent dark rifts cutting through luminous spiral arms. The core blazes with the light of billions of stars compressed into a relatively small region. And for the first time, the effect on Earth's night sky becomes noticeable in another way. The gravitational pull of Andromeda is beginning to affect the Milky Way's structure. Our galaxy's outer spiral arms are warping, pulled toward the approaching giant. Stars in our galactic halo have their orbits perturbed. Some are pulled toward Andromeda, others are flung outward. If anyone could still observe from Earth, or from whatever refuge humanity has fled to, the night sky would show two spectacular galaxies. The Milky Way stretching overhead as it always has, and Andromeda looming like a cosmic tidal wave about to break. The gravitational interaction is no longer theoretical, it's visible. The dance has entered its final phase. But let's focus on what's happening not to Earth's view, but to the galaxies themselves during this approach phase. Starting around 2 billion years from now, when the separation drops below 1 million light years, the gravitational effects intensify from subtle to severe. Tidal forces. Just as the moon raises tides on Earth's oceans, Andromeda's gravity begins raising tides in the Milky Way's structure. But instead of water sloshing back and forth, it's stars, gas clouds, and dark matter being pulled. The effect is strongest in the outer regions of both galaxies, where gravity's grip is weakest and stars are most easily perturbed. Long filaments of stars begin stretching from the Milky Way toward Andromeda, like cosmic fingers reaching across the void. Similar streams extend from Andromeda toward us. These tidal tails can stretch for hundreds of thousands of light years, longer than either galaxy's original diameter. We can see this process happening in other colliding galaxies. The Antennae galaxies, two spiral galaxies in the constellation Corvus, about 45 million light years away, show exactly this pattern. Two long tidal tails extend from the collision site, each containing billions of stars flung outward by gravitational forces. The Mice galaxies, NGC 4676, in Coma Berenices show similar tails. The Tadpole galaxy, UGC, has a tail stretching 280,000 light years behind it, the remnant of a past collision. These are our futures playing out right now in other parts of the universe. We're watching preview trailers of our own galactic destiny. Satellite galaxy disruption. Remember those 50-plus dwarf galaxies orbiting Andromeda and the Milky Way? During the approach phase, their orbits become chaotic. Some dwarf galaxies will be torn apart by tidal forces before the main collision even occurs. Their stars will be stripped away and scattered, forming new stellar streams in the space between Andromeda and the Milky Way. Others will be gravitationally accelerated, flung outward on escape trajectories that carry them into intergalactic space. They'll become rogue galaxies, wandering the cosmic void with no large galaxy to call home. Still others will spiral inward, caught between two massive gravity wells, their fate sealed. They'll be consumed, added to the mass of the merging system. The Large and Small Magellanic Clouds, those two dwarf galaxies visible from Earth's southern hemisphere, will face this fate. Current models suggest the Large Magellanic Cloud will collide with the Milky Way in about 2.4 billion years before the Andromeda collision. The Small Magellanic Cloud's fate is more uncertain, but it too will likely either be consumed or ejected. Dark matter-halo interaction. Here's something most visualizations don't show. The dark matter halos of both galaxies extend much farther than the visible stars. Andromeda's dark matter halo might extend 500,000 light years or more from its core. The Milky Way's halo is similar. This means that even though the visible galaxies won't collide for another 2 billion years after this point, their dark matter halos are already interpenetrating. Dark matter doesn't interact electromagnetically, it doesn't emit light, doesn't collide like normal matter. It only interacts gravitationally. So when the dark matter halos overlap, they don't collide in any conventional sense. Instead, they gravitationally perturb each other's orbits in complex ways. This creates a gravitational gradient, a tide, that affects the distribution of normal matter in both galaxies. Gas and stars feel this tide and respond, even though the dark matter itself passes through like a ghost. The collision, in a very real sense, has already begun. Not with light and fire, but with invisible gravitational fingers pulling and reshaping the space between us. The approach phase is a slow-motion catastrophe. Over 2 billion years, two massive galaxies draw closer, their gravitational embrace intensifying, their structures warping in response to each other's pull. But the slow build is about to end. In our next act, we witness the moment of first contact, when outer spiral arms interpenetrate, when gas clouds collide at hundreds of kilometers per hour second, when the largest starburst in local group history ignites the darkness. The approach is ending. The collision is beginning. Let's witness first contact. 3.75 billion years from now, the moment arrives. After 10 billion years of gravitational attraction, after 2 billion years of visible approach, after countless computer simulations and theoretical predictions, Andromeda and the Milky Way make first contact. But contact is a misleading word, because what happens next defies our everyday intuition about collisions. The outer spiral arms of both galaxies interpenetrate, passing through each other like two clouds of smoke merging in the air. Remember, galaxies are mostly empty space. The average distance between stars is about 4 light-years. Even in the densest regions of a galaxy's core, stars are separated by light months. When two galaxies collide, the stars themselves almost never physically collide. They pass by each other, sometimes within light weeks or light months, but rarely close enough to interact directly. The probability of our Sun directly colliding with a star from Andromeda is less than 1 in a trillion. So if stars don't collide, what does? Gas. And when gas clouds collide at 200 plus kilometers per second, nearly 1 million miles per hour, extraordinary things happen. The starburst begins. Gas clouds don't pass through each other like stars do. When two clouds of hydrogen and helium slam together at these velocities, they compress violently. This compression heats the gas to thousands of degrees. It also increases the density by factors of 10, 100, sometimes 1,000. And when gas clouds reach sufficient density, gravity takes over. They collapse under their own weight. Star formation begins. Not the slow, gradual star formation we see in normal spiral galaxies. Not a few stars per year scattered across thousands of light years. This is a starburst. Millions of stars forming per year across the collision zone. It's the largest episode of star formation the local group has experienced in billions of years. The first generation of collision-born stars are massive, tens or hundreds of times the mass of our Sun. They burn blue-white, ferociously hot, consuming their nuclear fuel at prodigious rates. Within a few million years, the blink of an eye on cosmic timescales, the most massive ones explode as supernovae. And those supernovae trigger more star formation. The shock waves from the explosions compress nearby gas clouds, causing them to collapse and form new stars. It's a chain reaction of stellar birth and death, spreading through the collision zone like wildfire through a forest. Within 100 million years of first contact, the space between what used to be the Milky Way and what used to be Andromeda is ablaze with billions of newly formed stars. What the sky looks like. If Earth somehow still exists at this point, and we'll discuss that possibility shortly, the night sky is transformed beyond recognition. There is no longer a night in the traditional sense. The sky never goes fully dark. The starburst regions, vast clouds of ionized gas lit from within by millions of young hot stars, glow with a diffuse blue-white radiance. Even the darkest patches of sky have a faint luminosity, like perpetual twilight. Andromeda and the Milky Way are no longer separate structures. They've merged into a single, chaotic tangle of stars, gas and light. The familiar constellations are gone. Stars have been scattered, redistributed, sent on new orbits by gravitational perturbations. Looking up, you'd see no distinct galactic structures at all. Just a sky filled with light. Thousands of new bright stars where none existed before. Vast glowing nebulae stretching across entire constellations. Dark dust lanes silhouetted against the luminous background. It would be, simultaneously, the most beautiful and most alien sky Earth has ever seen. Supernovae are exploding at a rate of several per year across the merged system, compared to maybe 1 per century in each galaxy before the collision. Each supernova releases as much energy as the Sun will emit over its entire 10 billion year lifetime, concentrated into a few months. The space between stars is flooded with high-energy radiation, X-rays, gamma rays and cosmic rays accelerated to nearly the speed of light. Any planetary system close to the collision zone would be sterilized. Atmospheres would be stripped away, oceans would evaporate. Complex organic molecules would be broken down into simple atoms. The collision zone is a stellar nursery and a planetary graveyard all at once. How long does first passage last? The actual interpenetration, the period when the two galactic disks are physically overlapping, lasts approximately 200 to 300 million years. That's how long it takes for two objects 100,000 plus light years across, moving at 200 kilometers per second relative to each other, to pass through each other. But the effects last much longer. The starburst continues for several hundred million years after the initial passage. Gas continues collapsing, stars continue forming, supernovae continue exploding, and then something else happens. Gravity pulls the galaxies back together. Now let's address the question everyone wants to know. What happens to Earth? What happens to the Sun, to our solar system, during this cosmic cataclysm? The answer is both reassuring and terrifying. The good news, we probably won't be destroyed. Direct stellar collisions are extraordinarily rare. The probability that the Sun physically collides with a star from Andromeda is roughly 0.0001%, 1 in a million. Even close encounters, passing within a light year, are unlikely, perhaps a few percent probability at most. The Sun itself will continue burning, Earth will continue orbiting. The physical integrity of our solar system is likely preserved. But preservation doesn't mean safety. The bad news: we might be ejected during the chaos of the collision. Gravitational forces are extreme and unpredictable. Stars pass close to each other, not close enough to collide, but close enough for their gravitational fields to interact strongly. This creates what's called a gravitational slingshot effect. When two stars pass near each other, they exchange momentum. One star gains velocity, the other loses it. It's the same principle NASA uses to accelerate spacecraft past planets, but operating on stellar scales. For individual stars, this can mean ejection, being flung out of the galaxy entirely. In 2008, astronomers T.J. Cox and Abraham Loeb at Harvard ran detailed computer simulations of the Andromeda Milky Way collision. They modeled the trajectories of millions of individual stars, including our Sun, through multiple passages. Their simulations suggested a range of possible outcomes, with probabilities varying depending on initial conditions and simulation parameters. Approximately 50% chance. The solar system remains within the merged galaxy, relocated to a different radius than we currently occupy, but still gravitationally bound to the system. Roughly 30% chance. The solar system is ejected to the extreme outer regions of the merged galaxy, 100,000 to 200,000 light-years from the center, far beyond the main stellar disk, in the sparse galactic halo. About 12% chance. The solar system is flung completely out of the merged galaxy into intergalactic space, becoming a rogue solar system wandering the void between galaxies. Approximately 3% chance. The solar system is captured by Andromeda's central regions during the collision, ending up much closer to the merged galaxy's core than we are now, a more dangerous location due to increased stellar density and radiation. Roughly 5% chance. Complete ejection from the local group entirely, sent on a trajectory that carries the solar system into the cosmic wilderness, eventually billions of light years from the nearest large galaxy. These percentages represent one set of simulations. Actual outcomes depend on many variables, including the exact trajectories, encounter timing, and the presence or absence of triangulum in the collision. Let's explore what each scenario means. Scenario 1. Remaining in the merged galaxy, approximately 50% chance. This is the most likely outcome. The Sun ends up somewhere in the merged elliptical galaxy Milkomeda, probably at a different radius than we currently occupy. If we're relocated closer to the center, the night sky becomes much brighter, more stars visible, galactic core prominent on the horizon. But also more dangerous, higher radiation levels, more frequent supernovae nearby, greater chance of close stellar encounters. If we're relocated farther out, the night sky becomes sparser, fewer stars visible, galactic core a distant glow, but quieter, safer, with less radiation and fewer disruptions. Earth, if it still exists as a solid body, continues orbiting the Sun. The Sun continues its life cycle uninterrupted. From the perspective of anyone on or near Earth, very little changes locally, except the view. The familiar constellations are gone, scrambled by gravitational interactions. The Milky Way band no longer stretches across the sky. We're no longer in a spiral galaxy with a visible disk. Instead, we see a spherical distribution of stars in all directions, denser toward the galactic center, sparser toward the edge. Scenario 2. Ejection to the galactic halo, roughly 30% chance. Now things get interesting and lonely. If the solar system is flung to the extreme outer regions of the galaxy, 100,000 plus light-years from the center, we enter the galactic halo. This is the sparse, spherical region surrounding the main galaxy, populated mostly by ancient red stars and globular clusters. The night sky becomes sparse. Where the current night sky shows thousands of visible stars, the halo night sky might show dozens. The galactic core becomes a distant fuzzy glow low on the horizon, interesting to look at, but distant and faint. The upside, peace and quiet. No supernovae nearby. No radiation storms. No close stellar encounters. The halo is the galactic equivalent of a cabin in the wilderness, isolated but safe. The downside? Isolation. If any other civilizations exist in the galaxy, we're now far from them. Communication becomes difficult, travel becomes impractical, we're cosmically isolated. Scenario 3. Complete galactic ejection, about 12% chance. This is where things get existentially strange. If the solar system is ejected from the galaxy entirely, we become a rogue solar system drifting through intergalactic space. The Sun continues shining, Earth continues orbiting, locally nothing changes, but the sky goes dark. The Milky Way, Milkomeda rather, becomes a distant fuzzy patch of light slowly receding behind us. Andromeda's remnant, the local group's dwarf galaxies, everything we've ever known as the galaxy, becomes distant and faint. Ahead lies darkness. Intergalactic space contains almost nothing, a few rogue stars, some wandering planets, hydrogen atoms so sparse that you might travel for light years between encounters. Mostly just empty space. The nearest galaxies become tiny, distant smudges, interesting to astronomers, but unreachable. We drift through the void at hundreds of kilometers per second, going nowhere in particular, with nothing but our own solar system for company. Is this terrifying, lonely, or strangely peaceful? That depends on perspective, but it would certainly be different. Scenario 4. Capture by Andromeda's core, approximately 3% chance. This is the dangerous outcome. If the solar system is captured by the central regions of the merged galaxy, we end up in a much denser stellar environment. Stars are separated by light months instead of light years. Close encounters become common. Supernova rates are higher. Radiation levels are elevated. Any planets in the habitable zone of nearby stars would be sterilized repeatedly. Long-term stability for complex life becomes questionable. This is the scenario we'd most want to avoid. Though by the time it matters, whether anyone is still around to care is another question entirely. But there's one more collision happening during all of this, and it's perhaps the most spectacular: the collision of the supermassive black holes. At the center of the Milky Way sits Sagittarius, a star, our central supermassive black hole, with a mass of approximately 4 million times that of the Sun. At the center of Andromeda sits M31, a monster black hole weighing in at 100 to 200 million solar masses, 25 to 50 times more massive than ours. When the galaxies collide, these two black holes are on a collision course of their own. But black holes don't collide quickly. They spiral inward over millions of years in one of the most complex gravitational dances in astrophysics, the spiral inward. After first passage, the two black holes are separated by hundreds of thousands of light years, roughly the original separation of the galaxies. They're both embedded in their respective galaxies' centers, surrounded by dense stellar populations. As the galaxies merge, these black holes begin spiraling toward each other, but they don't simply fall straight in. They orbit each other in an ever-tightening spiral, losing orbital energy through a process called dynamical friction. Here's how it works. As each black hole moves through the galaxy, it gravitationally attracts nearby stars. These stars are pulled along in the black hole's wake, forming a trailing density enhancement like a wake behind a boat. This trailing material exerts a gravitational drag on the black hole, slowing it down and causing it to spiral inward. Over tens of millions of years, the two black holes draw closer together. From a separation of 500,000 light-years, they close to 100,000 light-years, then 10,000, then 1,000. The final parsec problem. But then something interesting happens. When the black holes get to within about 1 parsec of each other, about 3 light-years, the spiral slows dramatically. This is called the final parsec problem. At this separation, there aren't enough stars in the immediate vicinity for dynamical friction to remain effective. The black holes have essentially scattered or consumed all the nearby stars. They're in danger of stalling at this separation for billions of years, orbiting each other endlessly without quite merging. Several mechanisms might overcome this stall. 1. Gas inflow. If large amounts of gas fall into the central region, which is likely during the merger given all the disrupted gas clouds, that gas can absorb orbital energy from the black holes, allowing them to continue spiraling inward. 2. Stellar interactions. In a dense enough stellar environment, stars on eccentric orbits can still interact with the binary black hole system, extracting energy and allowing the spiral to continue. 3. A third black hole. If Triangulum joins the collision, its central black hole, about 3 million solar masses, could interact with the binary system. Three-body dynamics are chaotic and can rapidly extract orbital energy, pushing the system toward merger. The final merger. Eventually, one way or another, the black holes get close enough that gravitational wave emission becomes dominant. When black holes orbit each other, they create ripples in space-time, gravitational waves that carry away energy. The closer they are, the stronger the gravitational waves and the faster they lose energy. Once the separation drops to a few light weeks, gravitational waves become strong enough to force rapid in-spiral. Over a period of perhaps a few thousand years, very fast by cosmic standards, the black holes spiral from light-week separation to light days, then light hours, then light minutes. The final phase happens fast. In the last second before merger, they orbit each other hundreds of times, each orbit faster than the last, spiraling together at an appreciable fraction of the speed of light. Then they merge. The gravitational wave event. The merger of two supermassive black holes creates the most powerful gravitational wave event the universe can produce short of the Big Bang itself. The merged black hole, now weighing approximately 110 to 210 million solar masses, is briefly deformed, oscillating like a struck bell as it settles into its final spherical shape. These oscillations emit gravitational waves that ripple outward through spacetime at the speed of light. If the laser interferometer space antenna, a planned space-based gravitational wave detector, is operational at that time, it will detect this event easily. In fact, it will detect the in-spiral phase for thousands of years before the merger, watching in real time as these two black holes spiral together. The energy released during the final merger is staggering. In a fraction of a second, the system releases more energy in gravitational waves than all the stars in the observable universe emit in light during that same fraction of a second. It's not an explosion. It's space-time itself ringing like a bell, and that ringing carries more energy than you can easily comprehend. What happens to nearby stars? Any stars within a few light years of the merged black hole are in for a rough time. The gravitational wave burst is strong enough that it could potentially perturb their orbits. Stars orbiting very close to the black holes might be ejected at high velocity. Hypervelocity stars flung out of the galaxy at thousands of kilometers per second. But for anything farther than a few light years away, including Earth, if we're still in the galaxy at all, the gravitational waves pass by harmlessly. We would feel nothing. They would stretch and compress space by a tiny fraction as they passed, but not enough to notice without sensitive instruments. The merger would be detectable, fascinating to study, and utterly spectacular in its implications. But it wouldn't affect daily life for anyone not already in danger from being near a supermassive black hole. The first passage is complete. The starburst blazes across what used to be two separate galaxies. The central black holes have begun their long spiral toward merger. Earth's fate, wherever we end up, is sealed. But the collision isn't over. It's barely begun. Because galaxies don't merge on first pass. Gravity pulls them back together for a second collision, a third, sometimes a fourth. Each passage more violent than the last. Each iteration removing more orbital energy until finally the two galaxies can no longer separate, until they become one. Let's witness the birth of Milkomeda. The first collision was spectacular, but it's not the end. It's just the beginning of a longer, more complex process. After the initial passage, the two galaxies don't simply merge and settle down. They pass through each other, emerging on opposite sides, their structures warped and distorted but still largely intact. And then gravity takes hold. Think of it like throwing a ball straight up. It rises, slows, stops, and then falls back down. The galaxies, having passed through each other, begin to slow as their mutual gravitational attraction pulls them back together. Approximately 1 billion years after first passage, so about 5 billion years from now, the second collision occurs. The second collision is, paradoxically, even though the galaxies are moving more slowly. Why? Because the galaxies are now significantly disrupted. The first passage stripped away their outer regions, created tidal tails hundreds of thousands of light years long, and scrambled their internal structure. They're no longer pristine spiral galaxies with organized rotation. They're messy, chaotic, wounded systems. When two wounded galaxies collide, the interactions are more direct and more destructive. Any gas clouds that survived the first passage without forming stars now collide again. This triggers a second starburst, smaller than the first, since much of the gas has already been consumed, but still significant. Millions more stars form in a compressed timeframe. The remaining spiral structure, whatever vestiges of the original arms still existed, is now completely destroyed. There's no longer any recognizable disk, no organized rotation, no clear structure at all, just a chaotic swarm of stars, gas and dust. The tidal tails grow longer. Material flung outward during the first passage continues moving, stretching the tails to over 1 million light years in length. Some of this material will eventually fall back into the system. Much of it will escape entirely, lost to intergalactic space. If Triangulum joined the collision during the first passage, it's now fully integrated into the chaos. Its stars are mixed with stars from both Andromeda and the Milky Way. Its central black hole is spiraling inward, adding to the complexity of the central dynamics. Third passage, the final act. But the galaxies still haven't fully merged. After the second passage, gravity pulls them together once more. The third collision, approximately 6 billion years from now, is the final act. By now, the galaxies have lost so much orbital energy to tidal interactions, stellar scattering and gravitational wave emission that they can no longer escape each other. After the third passage, they don't separate again. They spiral inward, their cores drawing closer and closer until they merge completely. Some computer simulations predict a fourth or even fifth passage before final merger, depending on the exact initial conditions and the presence or absence of Triangulum. But the outcome is always the same. Eventually, the two galaxies become one. The entire process, from first contact to final merger, takes approximately 3 to 4 billion years. That's roughly 1/3 of the time that has elapsed since the Sun was born. For the stars inside the galaxies, this is an eternity. For the galaxies themselves, it's a relatively quick transformation. And at the end of it, something entirely new emerges. 7 billion years from now, the merger is complete. What was once the Milky Way and what was once Andromeda are now a single entity. Astronomers have nicknamed it Milkomeda, a portmanteau of its two parent galaxies. But that's a placeholder name, a bit of whimsy in scientific papers. Whatever civilization exists at that time will surely give it a proper name. But regardless of what it's called, Milkomeda is something entirely different from what came before. Structure. From spiral to elliptical, Milkomeda is an elliptical galaxy, specifically a giant elliptical, one of the largest galaxy types in the universe. Gone are the graceful spiral arms that once characterized both parent galaxies. Gone is the thin rotating disk where star formation happened. Gone is the organized coherent structure. In their place, a roughly spherical or football-shaped swarm of stars with no preferred plane of rotation. Stars orbit the galactic center in every direction, up, down, sideways, at random inclinations. Some stars orbit clockwise, others counterclockwise. There's no collective rotation, no shared angular momentum. The galaxy spans approximately 200,000 to 250,000 light-years across, significantly larger than either parent galaxy individually, but not quite as large as the sum of their original diameters because some material was lost to tidal tails and ejected stars. Stellar population, old and young, mixed together. One of the distinctive features of Milkomeda is its mixed stellar population. Most elliptical galaxies in the universe are dominated by old red stars. They formed long ago, consumed their gas in ancient starbursts, and have been coasting ever since, slowly aging populations with no new stars being born. But Milkomeda is different. It contains ancient red stars from the original halos of both galaxies, stars 10 to 12 billion years old, formed when the universe was young. Middle-aged yellow stars like our Sun, stars 4 to 6 billion years old, formed during the peak period of star formation in both parent galaxies. Young blue stars formed during the collision starbursts, stars only a few billion years old, still burning hot and bright. This creates a complex color gradient. The core of Milkomeda glows yellow-orange from the concentration of middle-aged and old stars. But scattered throughout, especially in former collision zones, are pockets of blue-white young stars. In another few billion years, those blue stars will age and die, and Milkomeda will slowly become more uniformly red. But for now, it's a galaxy in transition, still showing the scars and aftermath, the central bulge. At the heart of Milkomeda sits a massive central bulge, a dense, nearly spherical region containing tens of billions of stars packed into a relatively small volume. This bulge formed from the merger of the two galactic cores. It's gravitationally dominated by the merged supermassive black hole, now weighing 110 to 210 million solar masses depending on whether Triangulum's black hole joined the merger. Within a few thousand light-years of the center, stars are separated by light months instead of light-years. This is a crowded, dangerous region. Close stellar encounters are relatively common. Supernova rates are elevated. Any planets in the habitable zones of stars this close to the center would face constant radiation exposure. But farther out, in what astronomers call the main body of the elliptical, conditions are calmer. Stars are separated by light-years, similar to the Milky Way's disk today. This is where most of the galaxy's stellar population resides: gas and star formation. Most of the gas that both galaxies contained has been consumed. The collision starburst turned it into stars, and the radiation and supernova explosions from those young massive stars heated and expelled much of the remaining gas. But some gas remains. It's settling into a rotating disk in the central region, remnant material that wasn't consumed during the collision, slowly coalescing under gravity. This gas will, over the next billion years, form new stars, not at the furious rate of the collision starbursts, but steadily, slowly. Milkomeda will continue to have some star formation for several billion years. Eventually, even this gas will be exhausted, and then Milkomeda will become what most elliptical galaxies are: a red and dead system containing only aging stellar populations with no new stars being born. But that future is still billions of years away. Milkomeda is both graveyard and nursery. And this is what's profound about Milkomeda. It's simultaneously a graveyard and a nursery. It's a graveyard for the Milky Way and Andromeda as they once existed. Those beautiful spiral galaxies, with their graceful arms and organized rotation, are gone forever. The familiar constellations humans knew for thousands of years, scattered. The astronomical reference frame of an entire civilization, erased. But it's also a nursery. New stars are forming from the remnants of the collision. New planetary systems are coalescing from the debris. New worlds are being born, worlds that might, billions of years from now, develop their own life, their own civilizations, their own astronomers looking up and wondering how their galaxy formed. Destruction and creation are not opposites in the cosmos. They're two sides of the same process. So let's return to the question of Earth. If our planet, or rather, the remnant of what was once Earth, survives the collision, where will it end up in Milkomeda? We have a 50% chance of remaining within the merged galaxy, a 30% chance of ending up in the outer halo, and a 12% chance of complete ejection. Let's focus on that most likely scenario, remaining within Milkomeda. Most likely, the outer region's computer simulations suggest that if we remain in the galaxy, we're most likely to end up in the outer regions, somewhere between 50,000 and 100,000 light-years from Milkomeda's center. This is significantly farther out than we are now. Currently, we're about 26,000 light-years from the Milky Way's center. In Milkomeda, we'd be 2 to 4 times that distance from the new galactic core. What does this mean for the view? The night sky from Milkomeda's outer regions, looking up from Earth, or from whatever space habitat humanity might inhabit by then, the sky would be sparse compared to what we see today. Currently, we see thousands of stars with the naked eye. We're embedded in the Milky Way's disk, surrounded by stellar neighbours. From Milkomeda's outer regions, we'd see far fewer stars, perhaps a few hundred bright enough to see without telescopes. The galactic core would be visible as a diffuse yellowish glow on the horizon, prominent but distant. Not the spectacular Milky Way band we see today stretching across the sky, but rather a concentrated region of light in one direction. Nearby stars would be displaced from their original positions. The familiar constellations, Orion, Ursa Major, Cassiopeia, would be completely unrecognizable. Stars that were once our close neighbours might now be on the opposite side of the galaxy. Stars from Andromeda might be our new nearest neighbours. If you could measure stellar velocities precisely, you'd notice something else. Stars are moving in random directions relative to each other. There's no coherent galactic rotation like we experience today. Some stars are moving towards you, others away, some passing by at angles. It's chaotic compared to the organised rotation of a spiral galaxy, but it would also be quiet. Far from the galactic centre, far from star-forming regions, far from supernova danger zones. A peaceful, sparse, stellar environment. If we're in the halo, 30% chance. If we ended up in the galactic halo, 100,000 plus light years from the centre, things would be even more sparse. The galactic core becomes a distant, fuzzy patch of light. Stars are few and far between. The nearest stellar neighbour might be 10 to 20 light years away instead of the current 4 light years, Proxima Centauri. But here's something interesting. From the halo, you'd have an incredible view of the entire galaxy. You could see Milkomeda's full structure spread out before you, a giant elliptical galaxy glowing with the light of hundreds of billions of stars. Astronomers in the halo would have an unprecedented vantage point for studying galactic structure, stellar populations, and dynamics. It would be the ultimate astronomical observatory location. Lonely, yes, but scientifically valuable. If we're ejected, 12% chance. And if we're ejected into intergalactic space, then Milkomeda becomes just another distant galaxy in the sky, interesting to observe, but no longer home in any meaningful sense. The night sky would be dark, truly, profoundly dark in a way that humans have never experienced. The darkest natural dark site on Earth today still has airglow and zodiacal light, but in intergalactic space there's nothing, just absolute blackness punctuated by distant galaxy smudges. It would be simultaneously peaceful and existentially isolating, the sun's state. But there's an important caveat to all of this. By 7 billion years from now, the sun has its own problems. The sun is currently 4.6 billion years old. In another 5 billion years, about the time of the Andromeda Milky Way collision, the sun will begin evolving off the main sequence. It will swell into a red giant, expanding to perhaps 100 times its current diameter. Mercury will be engulfed. Venus will be engulfed. Earth's fate is uncertain. It might be swallowed, or it might spiral outward just enough to avoid being consumed, ending up as a charred, lifeless rock orbiting a bloated red star. By 7 billion years from now, when Milkomeda is fully formed, the Sun will be a white dwarf, a dense, Earth-sized stellar remnant slowly cooling over trillions of years. Earth, if it still exists, will be a frozen, airless world orbiting a dying star. No atmosphere, no oceans, no life, just a cold rock in the darkness. So while it's interesting to ask where Earth will be in Milkomeda, the more important question is, where will humanity be? The merger is complete, Milkomeda is born. But this isn't the end of the story, because galaxies like stars and planets and civilizations are not eternal. They too have life cycles, endpoints, final states. And Milkomeda's future is intimately tied to the future of the universe itself, an expanding, darkening cosmos, where even galaxies will eventually go dark. But before we confront that cosmic twilight, we need to ask a different question. Can life survive this merger? And if so, how? Let's examine the possibilities. Now we need to confront the most important question of all. Can life survive this cosmic transformation? Not just Earth, the rock itself, but life. Consciousness, intelligence. Can biological or technological civilizations persist through a galactic collision, or is this an extinction-level event on the grandest possible scale? The answer is more nuanced than you might expect. The timeline problem. Let's start with the uncomfortable truth. Earth's biosphere will almost certainly not survive to see the collision. The collision occurs approximately 4 billion years from now. But Earth's habitability has a much shorter timeline. The Sun's luminosity increases by roughly 10% every billion years as it ages. This is a natural consequence of stellar evolution. As hydrogen fuses into helium in the core, the helium accumulates and the core contracts slightly, heating up and increasing fusion rates. This 10% increase might sound minor. It's not. Within 1 billion years, long before the collision, Earth's average temperature will have risen by 40 to 50 degrees Celsius due to the brightening sun. This triggers a runaway greenhouse effect. The oceans begin evaporating. Water vapor, a potent greenhouse gas, amplifies the warming further. More evaporation leads to more water vapor leads to more warming. By 1.5 billion years from now, Earth's oceans will be completely evaporated. The planet becomes Venus-like, a scorched, sterile rock with a thick atmosphere of water vapor and carbon dioxide, surface temperatures exceeding 100 degrees Celsius. By 3 billion years, still a billion years before the collision, Earth is definitively dead. No liquid water, no breathable atmosphere, no organic chemistry complex enough to support life as we know it. The collision happens to a corpse. So Earth's native biosphere, the bacteria, the plants, the animals, the ecosystems that evolved over 4 billion years, will be extinct long before Andromeda arrives. But that's not the end of the story, because by the time Earth becomes uninhabitable, humanity, or our descendants, will have had over 1 billion years to prepare. 1 billion years is an almost incomprehensible amount of time. For context, 1 billion years ago, Earth was inhabited entirely by single-celled organisms. Multicellular life hadn't even evolved yet. What could a technological civilization accomplish with 1 billion years of preparation? Unless humanity intervenes, if humanity, or whatever we evolve into, survives the next few thousand years without destroying ourselves, and if we continue developing technology for even a tiny fraction of that billion-year window, we would achieve capabilities that seem like magic by today's standards. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy usage. Type 1. Planetary civilization. Harnesses all energy available on a planet, roughly 10 to the 16th power watts. We're currently at about 0.73 on this scale, projected to reach Type 1 in 100 to 300 years. Type 2. Stellar civilization. Harnesses all energy from a star, roughly 10 to the 26 watts. This would involve megastructures like Dyson spheres or swarms. Timeline, perhaps 1,000 to 5,000 years if development continues. Type 3. Galactic civilization harnesses energy from an entire galaxy, roughly 10 to the 36th watts. This is speculative, but theoretically possible over millions of years. A Type 2 civilization, achievable within a few thousand years, with 1 billion years as a buffer, would have options we can barely imagine. Option 1. Stellar engineering move. Earth's orbit outward as the sun brightens. This isn't as crazy as it sounds. In 2001, astrophysicists Gregory Laughlin and Fred Adams proposed using gravitational assists from asteroids to slowly spiral Earth outward. The idea: redirect large asteroids on precisely calculated trajectories so they pass near Earth, transferring momentum. Each passage nudges Earth's orbit slightly outward. Over millions of years, with thousands of precisely timed assists, you could relocate Earth to a safer orbital distance. This would extend Earth's habitability by billions of years, allowing the biosphere to persist through the collision era. Option 2. Terraform other worlds. Mars becomes habitable within a few hundred years using current or near-future technology. The moons of Jupiter and Saturn, Europa, Enceladus, Titan, could be colonized and terraformed over longer timelines. By the time Earth becomes uninhabitable, humanity could be spread across dozens of worlds in the solar system. The collision would affect all of them, but the risk is distributed. Some worlds might be ejected, others might remain, but humanity survives as long as one of them does. Option 3. Interstellar migration. With a billion years of preparation, humanity would almost certainly be an interstellar species. We'd have colonies around hundreds or thousands of nearby stars. The collision affects our specific solar system, but not those colonies. Even if the Sun is ejected into intergalactic space, our descendants around other stars continue thriving. From this perspective, the collision becomes almost irrelevant to humanity's survival. It's a local event affecting one star system among thousands we inhabit. Option 4. Post-biological existence. This is speculative, but over billion-year timescales, it's worth considering. Humanity might not be biological anymore. We might upload consciousness into computational substrates. We might merge with artificial intelligence. We might become something entirely different, digital beings living in vast computer networks. Von Neumann probes exploring the galaxy, distributed intelligences spanning light years. For post-biological entities, the collision becomes an opportunity. The chaos provides raw materials, energy, and new environments to exploit. A starburst is a massive energy source. A disrupted galaxy is a frontier to explore and colonize. Let's think about this differently. Let's stop thinking of the collision as a disaster and start thinking of it as an opportunity for a sufficiently advanced civilization. And remember, we're talking about a billion years of development time. The Andromeda Milky Way collision could be the most significant event in that civilization's history. And not because it's threatening, but because it's transformative. A galaxy being reborn. During the collision, millions of new stars form every year. These stars have planets. New planetary systems are coalescing from the gas and dust of the collision zones. For an interstellar civilization, this is a bonanza. Fresh worlds, uncolonized territories, raw materials in abundance, energy sources everywhere you look. If humanity has spread across the galaxy by this time, and a billion years is more than enough time to colonize the entire Milky Way several times over, even at modest sublight speeds of 1 to 10% the speed of light, then the collision provides access to Andromeda's territory as well. Suddenly, the explorable galaxy isn't 100,000 light-years across with 200 billion stars. It's 200,000 plus light-years across with over 1 trillion stars. The real estate has increased by a factor of 5. Stellar engineering opportunities. The collision will disrupt thousands of planetary systems, potentially leaving planets orphaned, ejected from their home stars, wandering as rogue planets through interstellar space. For an advanced civilization, these rogue planets aren't disasters. They're opportunities. Capture them, relocate them to stable orbits, terraform them, colonize them. The collision will create hundreds of thousands of new stellar binaries and multiple star systems as stars pass close to each other and become gravitationally bound. These systems are different from single star systems like ours. They have unique dynamics, different habitable zones, different possibilities for planetary engineering. The collision will trigger massive star formation, creating thousands of short-lived luminous O and B-type stars. These stars burn out quickly, but while they exist, they're powerhouses. potentially harvestable energy sources for a Kardashev Type 2 or 3 civilization. Scientific opportunity. From a pure knowledge perspective, witnessing a galactic collision from inside the collision is an unparalleled scientific opportunity. You could study star formation in real time on scales impossible in a quiet galaxy. You could observe black hole dynamics during the merger. You could measure gravitational wave signals directly from the binary black hole system as it spirals inward. You could test theories of galactic dynamics, dark matter behavior, and large-scale structure formation with observational data that would be impossible to obtain any other way. For a civilization that values knowledge, the collision isn't a threat, it's the event of the eon. The dark side, dangers remain. But let's not romanticize this too much. The collision does present genuine dangers, even for advanced civilizations. Supernova bombardment. The starburst creates thousands of supernovae per year for millions of years. Any planetary system within a few hundred light years of these explosions faces intense radiation. Atmospheres could be stripped. Biospheres could be sterilized. A spacefaring civilization could avoid this by relocating populations away from starburst zones, or by building radiation shielding. But it's a challenge. Stellar encounters. Even though direct stellar collisions are rare, close encounters become more common. A star passing within a light year of your home system could destabilize planetary orbits, sending comets and asteroids cascading into the inner system. Again, manageable with technology, you can predict encounters and either relocate or deflect the threatening objects. But it's a persistent danger requiring constant vigilance. Gravitational chaos. The chaotic gravitational environment during the collision makes long-term planning difficult. Stellar orbits are unpredictable. Gas and dust distributions shift rapidly. What looks like a safe region might become dangerous within a few million years. A civilization would need to be nomadic, flexible, ready to adapt to changing conditions rather than settling permanently in one location. But remember the timescale. And here's the critical factor. We have time to prepare. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy usage. Type 1, planetary civilization, harnesses all energy available on a planet, roughly 10 to the 16th power watts. We're currently at about 0.73 on this scale, projected to reach Type 1 in 100 to 300 years if current growth continues. Type 2, stellar civilization, harnesses all energy from a star, roughly 10 to the 26th watts. This would involve megastructures like Dyson spheres or swarms. Timeline, perhaps 1,000 to 5,000 years if exponential development continues, though these timelines are highly speculative. Type 3, galactic civilization, harnesses energy from an entire galaxy, roughly 10 to the 36th watts. This is purely theoretical and would require millions of years or more. A Type 2 civilization, potentially achievable within several thousand years, if technological progress continues exponentially, though this remains speculative, would have options we can barely imagine with a billion-year preparation window. The verdict: survivable, but challenging. The collision is survivable for a technological civilization with sufficient preparation time. The billion-year warning is more than adequate, but survival isn't passive. It requires action, relocating populations, engineering orbits, building redundancy into infrastructure, spreading across multiple star systems, adapting to a dynamic and unpredictable environment. For a civilization that embraces these challenges, the collision becomes a defining event, a cosmic rite of passage marking the transition from a single galaxy species to something larger and more ambitious. For a civilization that fails to prepare, or that stagnates technologically, the collision could be genuinely catastrophic. The question isn't, can life survive? The question is, will we choose to survive? We've traced the collision from its slow approach through first contact, multiple passages, and final merger. We've seen Earth's probable fates. We've explored how life, especially intelligent technological life, might not just survive but thrive. But Milkomeda's story doesn't end 7 billion years from now. Galaxies, like stars, have life cycles that extend far beyond their formation, And Milkomeda's far future is intimately connected to the future of the universe itself, an expanding, darkening cosmos moving inexorably toward its final state. Let's look further ahead. Not billions of years, but tens of billions. Not to Milkomeda's middle age, but to its twilight and beyond. Let's witness the far future. Let's step back, way back. Let's look at Milkomeda not from within, but from the perspective of the universe itself. 10 billion years from now, roughly 6 billion years after the merger completes, what does the universe look like? And where does Milkomeda fit into it? The answer is both humbling and profoundly lonely. The expanding universe. The universe has been expanding since the Big Bang 13.8 billion years ago. But around 5 billion years ago, roughly when Earth was forming, something changed. The expansion began accelerating. This acceleration is driven by something we call dark energy, a mysterious property of space itself that acts like a repulsive force, pushing everything apart. We don't know what dark energy is, we don't understand its nature, but we can measure its effects, and those effects are profound. As the universe expands and accelerates, the distance between galaxy clusters grows. And because space itself is expanding, distant objects eventually recede from us faster than the speed of light. Not because they're moving through space that fast, but because the space between us is stretching faster than light can cross it. This creates a cosmic horizon, a distance beyond which objects are fundamentally unobservable because their light can never reach us. 10 billion years from now, this horizon has moved inward. Galaxies that are visible to us today will have crossed the horizon and disappeared from view. The disappearing universe. Right now, from Earth, we can observe roughly 2 trillion galaxies spread across 93 billion light-years of observable universe. The Hubble Deep Field, the James Webb Space Telescope deep images, they show us a cosmos teeming with galaxies in every direction. But 10 billion years from now, from Milkomeda, the view is dramatically different. The Virgo supercluster, the massive collection of galaxy clusters that the local group is falling toward, has receded beyond the cosmic horizon. Its light, redshifted by expansion, has faded into undetectability. The Coma cluster, the Perseus-Pisces supercluster, the Sloan Great Wall, all the large-scale structures we map today, gone. Not destroyed, just receded beyond observability. Within 100 billion years, only the local group, now merged into Milkomeda and a handful of survivor dwarf galaxies, will remain visible. Everything else will have vanished beyond the horizon. Future astronomers in Milkomeda looking at the sky with their most powerful telescopes will see almost nothing. A handful of dwarf galaxies orbiting Milkomeda. And beyond that, darkness. They'll be living in an island universe cosmically isolated, with no evidence that anything exists beyond their own galaxy. The lost evidence. And here's something truly unsettling. Future civilizations in Milkomeda will have lost the evidence for the Big Bang. Right now, we can observe the cosmic microwave background, the afterglow of the Big Bang, still detectable 13.8 billion years later. It's our smoking gun evidence that the universe had a hot, dense beginning. But the CMB is redshifting due to cosmic expansion. The wavelengths are stretching, the temperature is dropping. Currently, it's at 2.7 Kelvin. In 100 billion years, it will be redshifted into undetectability, cooler than the faint heat of stars, impossible to distinguish from background noise. Future astronomers will look at the sky and see a single large galaxy, a few dwarf companions, nothing else. No distant galaxies, no cosmic microwave background, no evidence of expansion, no evidence of a Big Bang. They might develop the same cosmological theories we have, maybe through mathematical reasoning or philosophical arguments, but they'd have no observational proof. They'd be doing cosmology with one hand tied behind their backs. We're living in a special epoch, late enough that structure has formed and galaxies exist, but early enough that we can still see the cosmic web, still detect the CMB, still observe the expansion of the universe. In cosmic terms, we're living in the golden age of observational cosmology, and it's ending. But let's keep going. Let's follow Milkomeda's evolution not just billions but trillions of years into the future, because galaxies, like everything else in the universe, are not eternal. The last star-star formation in Milkomeda continues for a while. Gas continues collapsing, new stars continue forming, but the gas supply is finite and not being replenished. There's no new gas falling in from intergalactic space, no mergers with other galaxies bringing fresh material. By about 100 billion years from now, 90 billion years after the merger, the last star forms in Milkomeda. It's probably a small red dwarf, a star with only 10 to 20% of the Sun's mass. These stars burn slowly, efficiently, living for trillions of years. But it's the last one. After this, no more stars will ever form in Milkomeda. The galaxy enters its twilight age, the age of red dwarfs. For the next several trillion years, that's trillion with a T, far longer than the current age of the universe, Milkomeda is illuminated by red dwarf stars. These stars are dim, cool, and incredibly long-lived. The smallest red dwarfs can burn for 10 trillion years or more. During this time, they provide stable, albeit faint, illumination to any planets still orbiting them. This is called the stelliferous era, the age of stars, and it lasts a very, very long time. But all stars eventually exhaust their fuel, and red dwarfs, despite their longevity, are no exception. By about 10 to 20 trillion years from now, even the longest-lived red dwarfs have burned through their hydrogen fuel. They cool and fade, becoming white dwarfs, dense, Earth-sized stellar remnants that emit only residual heat. The last star in Milkomeda goes dark. The degenerate era. After the last star dies, Milkomeda enters what cosmologists call the degenerate era, an age dominated by stellar remnants. The galaxy is now a swarm of white dwarfs, cooling slowly over trillions of years, neutron stars, dense remnants of supernova explosions, black holes, stellar mass black holes from the most massive stars, brown dwarfs, failed stars that never ignited fusion, planets, still orbiting their dead stars, frozen and dark. These objects continue orbiting the central supermassive black hole, now the dominant gravitational influence in the system. The galaxy still exists in a sense. It's still a bound system, but it's dark, silent, a graveyard of dead stars, and it gets stranger. Black hole evaporation. Stephen Hawking predicted in 1974 that black holes aren't truly black. Due to quantum effects at the event horizon, black holes emit radiation, now called Hawking radiation. This radiation carries away mass energy, causing the black hole to slowly evaporate. For stellar mass black holes, this process is absurdly slow. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate. That's 1 followed by 67 zeros. Far, far longer than the current age of the universe. But given enough time, even these timescales become relevant. By 1 Google years from now, a timescale that makes trillions look like nothing, even the supermassive black hole at Milkomeda's center will have evaporated completely. What remains? Scattered electrons, positrons, photons and neutrinos. No stars, no planets, no black holes, just a diffuse cloud of elementary particles, slowly spreading through an ever-expanding space. The galaxy, in any meaningful sense, has ceased to exist. Heat, death. This is the final fate of not just Milkomeda, but the entire universe. Heat, death. All energy gradients equalized. No stars shining. No black holes radiating. Just a cold, dark, maximally entropic state where nothing can happen because there's no available energy to make things happen. It's not dramatic. It's not explosive. It's just fading. A universe that slowly, inexorably, runs down like a clock that no one winds. But before we sink too deep into cosmic pessimism, let's zoom back out and remember, the Andromeda Milky Way collision isn't unique. Galaxy collisions are happening throughout the universe right now. The antennae galaxies. 2 spiral galaxies in the constellation Corvus, about 45 million light-years away, currently in the middle of their collision. We can see the spectacular tidal tails, long streamers of stars stretching hundreds of thousands of light-years from the collision zone. This is our future, happening in real time somewhere else. The Mice galaxies. In the constellation Coma Berenices, about 290 million light-years away. two spirals with prominent tails caused by tidal forces. The name comes from the resemblance to two mice, each with a long tail trailing behind. The Tadpole Galaxy, in the constellation Draco, about 420 million light-years away. This galaxy has a tail stretching 280,000 light-years, longer than the Milky Way's entire diameter. The tail formed when a smaller galaxy punched through the disk, pulling stars behind it like a wake behind a boat. Stephan's Quintet, a group of 5 galaxies in the constellation Pegasus, about 280 million light-years away. 4 of them are interacting gravitationally, colliding and merging. The James Webb Space Telescope's first images included a spectacular view of this system, showing shock waves from the collision heating gas to millions of degrees. ARP 220, 2 gas-rich spiral galaxies in the final stages of merging, about 250 million light-years away in the constellation Serpens. The merger has triggered an enormous starburst. ARP 220 is one of the most luminous galaxies in the nearby universe, forming stars at hundreds of times the Milky Way's current rate. These aren't rare exceptions. Galaxy collisions are common. In the observable universe, thousands of major galaxy mergers are happening at any given moment. We can observe every stage of the process: early approach, first contact, chaotic merger, final elliptical product, just by looking at different systems. The Andromeda Milky Way collision is just one example of a universal process. Galaxies interact, merge, grow, and transform. It's part of the natural life cycle of cosmic structure. What makes our collision special is that it's our collision. It's happening to the galaxy we call home, involving the stars we can see with our own eyes. But in the grand scheme of the universe, it's perfectly normal, ordinary, expected. And that's somehow comforting. We're not being singled out by some cosmic malice. We're just participating in the natural evolution of the universe. We've journeyed from 4 billion years in the future to Google years. Timescales so vast they lose all meaning. We've watched Milkomeda form, age, and ultimately fade into heat death alongside the rest of the universe. It's easy to feel small in the face of such timescales, to feel like nothing matters if everything ends in darkness anyway. But I want to challenge that perspective, because there's something profound about existing right now, in this specific moment of cosmic history. Something precious about being here to witness, to understand, to comprehend. Let's bring this cosmic journey back to Earth. Back to you, back to the present moment, and what it means to be conscious in a universe destined for collision, merger, and eventual heat death. Let's talk about meaning. Alright, let's come back to Earth. Let's come back to you. You won't live to see the Andromeda collision, neither will your children, nor their children, nor their children for 50 million generations. 4 billion years is incomprehensible. It's 50,000 times longer than recorded human history. It's longer than the entire history of complex life on Earth. Yet it's real. It's happening. While you've been watching this video, Andromeda has moved 300 kilometers closer. By the time you go to sleep tonight, it will be another 10 million kilometers nearer. The future is already in motion. The collision has already begun, just slowly, imperceptibly, over timescales our minds weren't designed to grasp. But here's what strikes me as profound. You exist at the perfect moment to know about this. The Golden Age. Think about the timing. You're living late enough in cosmic history that galaxies exist, that stars have formed and died multiple times, that heavy elements have been created, that planets and life are possible. But you're also living early enough that the universe is still young, still full of visible galaxies, still expanding but not yet empty. You exist during the brief window, cosmically speaking, when the Milky Way and Andromeda are separate structures. In the deep past, they were closer, not yet differentiated from the cosmic web. In the deep future, they'll be merged. But right now, in this era, they exist as 2 distinct, majestic spiral galaxies sharing the same cosmic neighborhood. You're living during the last age when someone can look up at the autumn sky and see Andromeda as a separate galaxy. In a few billion years, that won't be possible anymore. You're also living in the golden age of cosmology. We can see the cosmic microwave background, map the large-scale structure of the universe, observe distant galaxies billions of light years away. Future civilizations will lose this. The evidence will fade beyond detectability. We have something they won't have. The ability to see our cosmic context clearly. That's not insignificant. That's precious. What this means. So what do you do with this knowledge? You could choose nihilism. Everything ends in heat death anyway. Nothing matters. We're all doomed. But I'd argue that's precisely backwards. The fact that everything is temporary, stars, galaxies, even the universe itself, doesn't make it meaningless. It makes the present moment more significant, not less. You exist, right now, conscious, aware, capable of understanding that in 4 billion years, two galaxies will collide, capable of contemplating timescales that dwarf human history, capable of comprehending your place in a story that stretches from the Big Bang to heat death. That capacity, consciousness that can understand its own cosmic context, is rare, possibly very rare. We don't know if other civilizations exist, but we know we exist. We know we can comprehend this, and that's remarkable. The responsibility. This understanding create responsibility? I think it does. Not a religious or moral responsibility imposed from outside, but a practical one that emerges from the facts themselves. If we're living during a golden age of cosmic observability, the brief window when the universe can be studied and understood, then we have a responsibility to do that studying, to observe, to measure, to understand, to preserve that knowledge. If there's a chance, even a small one, that intelligent life is rare and that we might be among the few conscious beings in the cosmos, then we have a responsibility not to waste that rarity, not to destroy ourselves through war, environmental collapse, or technological recklessness before we've had a chance to become what we might become. If we have 4 billion years before the collision, and if technological civilizations can reach the stars in mere thousands of years, then we have a responsibility to survive long enough to see what we might achieve with all that time. Not because some cosmic authority demands it, but because the alternative, extinction before we've barely started, would be a waste of something potentially precious. One final thought before we part ways. Tonight, when you go outside, look up. If you're in a dark location, away from city lights, look toward the constellation Andromeda. That faint smudge you might see, if your eyes are good and the sky is clear, is your future. Right now, it's a distant neighbour. In 4 billion years, it will be family. The journey connecting those two states, distant neighbour to merged family, has already begun. Every second, Andromeda draws 110 kilometres closer. Every day, nearly 10 million kilometres. Every year, 4 billion kilometres. The distances are so vast that the motion seems imperceptible, but it's as inevitable as sunrise, as certain as the seasons, as inescapable as entropy. Nothing can stop it. No force in the universe is strong enough to halt the gravitational attraction between two massive galaxies that have been falling toward each other for billions of years. But nothing can stop it doesn't mean nothing can be done about it. If humanity survives, if we don't destroy ourselves in the next few centuries, we'll have time. Vast, almost incomprehensible amounts of time. Time to spread across the solar system. Time to reach other stars. Time to become something we can barely imagine from our current vantage point. 1 billion years of technological development doesn't just change what we can do, it changes what we are. Whether we remain biological, become post-biological, merge with our machines, or transform into something entirely different. By the time the collision arrives, humanity might be as different from us as we are from the first single-celled organisms. And that future humanity, those distant descendants or successors, might not see the collision as a catastrophe at all. They might see it as an opportunity, a chance to explore a galaxy reborn, a frontier of newly formed stars and fresh worlds, a cosmic spectacle to witness from the inside. The collision might be the best thing that ever happened to them. We can't know. We can only ensure they have the chance to find out. Your place in this story. And you, watching this right now, you're part of this story, not the collision itself. You won't live to see that. But you're part of the prelude. Part of the civilization that first learned this collision was coming, first calculated the timeline, first imagined what it might mean. You're living in the era when humanity transitioned from looking at Andromeda and seeing just a fuzzy patch of light to understanding what it is, where it's going, and what it means for our cosmic future. That transition, from ignorance to understanding, is itself a kind of collision. Not of galaxies, but of consciousness meeting reality, of curiosity encountering truth, of small, finite minds glimpsing something vast and timeless. And that collision, the one happening right now, in your mind, as you comprehend what's coming, that's a beautiful thing. If you've made it this far, thank you. And in 4 billion years, it won't be 2 galaxies anymore. It will be one, Milkomeda, a new structure born from collision, chaos and transformation. But that's 4 billion years from now. Right now, at this moment, on this night, you can still see them as separate. You can still look up at Andromeda and know, that's not us. Not yet. Someday it will be. Subscribe if you want more journeys through deep time and cosmic futures. Comment with your thoughts. Does this future feel threatening, exciting, or simply inevitable? And tonight, seriously, tonight, go outside and look up. Find Andromeda in the autumn sky. That fuzzy patch is real. It's approaching. And now you know what it means. The future is vast. The future is beautiful. And it's coming, ready or not. Welcome to tomorrow.